Suppose you consider the end A of the conductor is too very high potential, that is A end possess higher potential than that of the B end. Each resistor carries V1 potential, V2 potential and V3 potential. So this is a sentence what I framed myself just by looking at this diagram. When number of resistors is connected in series, the equivalent resistance is equal to the sum of individual resistance. Hello everyone, I am Brinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 4 of chapter 3, and chapter name is Current Electricity. So today in this class, let us just deal with the resistance at certain temperature concept and about the power laws by using a power laws formula. Then let us just see about the resistance when it is connected in series, how is the formula given, and when it is connected to parallel, how is that we calculate the resistance, as well as the cells, EMF and internal resistance means what. These are the concepts what we study in today's concept class. So here we have about the variation of resistance with temperature. How does the variation of resistance with temperature takes place? That is a linear curve. Okay, so now we have that the dependence of the resistance on temperature is same as that of the dependence of resistivity on the temperature, because our formula is that R is equal to rho into L divided by A. These two are having the proportionality concept, that is the way R, that is a resistance, capital letter R, which is termed to be a resistance, depends on the temperature. In similar way, the resistivity that is given as rho also depends on the temperature. Now we know that the dependence is a linear. So according to that linear concept, we have got an equation, call it as the resistance at certain temperature can be equated as the resistance at original temperature into 1 plus alpha into T minus T naught, and this is one set of equation. Suppose if you consider RT is the resistance at certain temperature, R naught is the resistance at zero temperature, and this is a standard temperature what we are considering, because R naught means it is 0 degrees Celsius. That means according to standard temperature it is 273 degree Kelvin. So what happens now? So when T temperature is 0 degrees Celsius, the complete T naught terms cancels out. So we have R naught into 1 is R naught plus R naught alpha and T. So here at this point T naught is cancelled out, because T naught is the temperature, initial temperature, and initial temperature is said to be 0 degrees Celsius. So the value is 0 for T naught, that is why that the last term gets cancelled. So we have this term with us. So what is the next position that we are doing? We are wanting to have the coefficient of resistivity. Coefficient of resistivity at certain temperature of a metallic conductor has to be known. So it is, we are supposed to keep R alpha at one place. So what happens? This goes to other side. So it becomes RT minus R naught, and the whole term R naught into T. This and this comes to the denominator. So we have R naught into T is the temperature. So this is the way of finding out the coefficient of resistivity formula. So this alpha is nothing but the one which shows the coefficient of resistivity, because of which we can calculate the actual resistance of the metallic conductor. So how do you define the coefficient of resistivity at certain temperature of a metallic conductor? It is defined as increase in the resistance per unit original resistance per unit rise in degrees Celsius. That is, for each rise in degrees Celsius, that is for each and every value of temperature, there is increase in the temperature, which increases the resistance of the material from that of the original resistance, is known as the coefficient of resistivity. That is, when the temperature is increased from original temperature to some high temperature, there is increase in the resistance also from the original resistance to higher value of resistance. That is all about your coefficient of resistivity concept. So you will have to know the equations, that's all. It is not like you will have to study the whole complete derivation. So next, coming to electrical energy and power. Hope you all know what is meant by electrical energy. That is the energy which is liberated by the electrons when it moves from negative of the circuit, that is negative terminal of the circuit, there is an electron which is getting drifted, because of which there is something called as energy, and that energy is nothing but the electrical energy. So here we'll have to consider, all of you will have to consider certain diagram when it comes to the derivation. Only then you will get to know what exactly is happening over there, why it was derived, why this equation arises, why is that we have to consider some other equations in between this derivation. So all those have got a simple and a single solution, that is just imagine by plotting the diagram over there. Okay, so we have, consider a conductor which is having a length L. So there is a conductor which has a length, call it as L. Okay, in which a current I is flowing from one end to the other end. The electric potential at A, suppose this is A area and this is B area. From A area there is a potential of VA. And from B area there is a potential of VB. So this end and this end are having certain potential, call it as VA as well as VB. Therefore, the potential difference between the ends of the conductor, how is it given? Suppose you consider the end A of the conductor is too very high potential, that is A end possess higher potential than that of the B end. So how is that you are giving? Potential is equal to the potential difference is VA minus BE, higher minus lower. Call it as this equation as 1. So call this equation as 1. Now we have the charge. Only when the charge is moving or charge is flowing, we have a current I. Therefore, we have potential also called as V. And we have given the potential difference. Suppose if there is a flow of charge, call it as delta Q is equal to I into delta T. If suppose delta Q is I into delta T, that is current is equal to charge flowing per unit temperature. On changing the sequence, you will get delta Q is equal to I into delta T. Then suppose at the end of A end, there is a potential of VA, then the charge which is flowing through it can be given as VA into delta Q. Similarly, at VB, that is at end B, we have VB is equal to delta Q. So we have two equations at one end and at the other end, at end A and at end B. So now it is our duty to check out on the potential energy. So how do you check out on the potential energy? It will be like delta U, that is change in potential energy, is equal to, when you give the exact potential energies formula, it is like second end minus first end, VA minus VB. On substituting for these two, we have, that is VB along with its charge, it is VB into delta Q, and VA along with its charge, it is VA into delta Q. So delta Q is a common term, so it can be VB minus VA. So we have into delta Q. So VB minus VA is nothing but the opposite of this, so it will be minus V. So which is equal to minus of V into I into delta T. I am substituting this for delta Q value. So delta U, that is change in potential energy, is negative. That means decrease in potential energy is nothing but increase in the kinetic energy. Always potential energy acts opposite to that of the kinetic energy. So I can just write this as, since delta change in kinetic energy is equal to delta U, that is minus delta U. When you just equate it, it becomes positive because minus into minus of this equation becomes plus of this equation. So it is kinetic energy is equal to V into I into delta T. So we have this much of concept with us now. Now consider the power. So how do you convert a power? Power means it is delta W divided by delta T. Kinetic energy can be replaced as the work done because it is work what is being done, which is the result of the potential energy. Work done is nothing but the kinetic energy. Okay, potential energy means the one which stores the work. And work is being done means it is getting transferred itself from potential energy to the kinetic energy. So the same thing is happening over here. So delta W becomes Vi delta T divided by delta T. Delta T cancels. So what remains is P is equal to V into I. Having this P is equal to V into I, we are getting into the power loss equation. How do you get into power loss equation? So the power loss equation, we have the equation as P is equal to V into I. So we have P is equal to V into I equation over here. Okay, and we know that V is equal to I into R by Ohm's law. So I can write this as P is equal to I into R into I. So it can be written as I square into R, and it is P. So we also know that if you retain your I there, it is V divided by R. So I can just equate in the place of I as P is equal to V square divided by R square into R. R square cancels with R. So what do we have? P is equal to V square by R. So this equation equates the power loss or the ohmic loss. It is also called as ohmic loss because we use Ohm's law equations over here. Okay. So it is nothing but when the transformer is there, that is a power station is present. You can see in this image, the power station is present over here. But when the circuits, that is the electrical energy, keeps on moving through the circuit and over a longer and longer distance, it reduces its power. There is a loss due to the transmission. Finally, we acquire a little amount of the electrical energy for our domestic use. That is nothing but the power loss which is happening now and then. Okay, so that is all about this concept, why this equation was derived, because in order to know the power loss, and this is called as a power loss equation where P means power, V means potential energy, R means the resistance. So here ends our electrical energy and power topic, and next we are going to cells which is connected in series as well as in parallel. So here series resistance, you know how there is a resistance which is given. So resistance is given in this symbol and the change in resistance given by this arrow mark. Now we are talking about the fixed resistance which is having certain value, that is a carbon resistor is what we use, and this is much and much important on the exam point of view for your practical examinations as well. So here we have a battery. If it is only one, it is known as cell. If it is a collection of cell, it is known as a battery, which provides certain potential energy due to which there is flow of charges and current is produced over there. So here this combination of resistors in series, that means there is chain link between all the resistors which is connected in this format. Okay, and combination of resistor in parallel means one below the other as per this, because we have three connections over here which is divided, so there is one below the other connection which is called as a parallel. So now it is our duty to derive the equation in order to know how to calculate the resistance in series as well as how is the calculation of resistance in parallel combination. So combination of resistors in series. So we have a cell which is connected to a series resistance, and this is producing a current of I. So I is produced here. This is R1, R2 and R3, and there is a potential for each and every resistors. Call it as V1, V2, V3. There is a different potentials for each resistors. Okay. So now we will have to calculate. Before calculating, we'll have to know. That is, by looking at this diagram, you can say that consider a circuit connection in which R1 resistor, R2 resistor and R3 resistor, three resistors are connected in series, which is externally connected to a cell of certain potential difference, call it as V. Each resistor carries V1 potential, V2 potential and V3 potential. So this is a sentence what I framed myself just by looking at this diagram. So even you people also can do the same thing, correct? That is just the description whatever you give. Now what is that you can see? You can see I and V. So what is the statement will you give for I as well as V? It is like I is the current which is flowing through the circuit and it is same throughout. So same I flows throughout the circuit. But potential V is nothing but sum of potential difference of each circuit. Okay. So we have first point, call it as same I, that is current, flows through the circuit. This is a circuit. Okay, this is a symbol of circuit, how we write it. Okay, next is total potential energy is equal to sum of potential difference across each resistor. Okay, that is, we have V is equal to V1 plus V2 plus V3. Okay, so we know that according to Ohm's law, we have V is equal to I into R. So how can I write this? In the place of V1, V2, V3, this I have got by the second point. I can write it as V is equal to, you are not supposed to substitute anything for the left hand side. So V1 is I into R1 because I is the same current which is flowing, so it is constant. Nothing like 1, 2, 3 for I. For V2 you have plus I into R2 plus I into R3. Take the common out. V is equal to I into R1 plus R2 plus R3. So we have this equation with us now. Now we will have to convert, that is convert the series connection of circuit into a equivalent resistance which is having the same value as that of when it is connected in case of series. So I'll just replace the whole circuit by one cell and one resistance such that the resistance R1 plus R2 plus R3, whatever value it has, the same valued resistance I'll be taking and placing it over here. So we have to check the combination of resistors in series formula now, how it goes. So it is like this is a battery, call it as B and B. So here we have a resistance, call it as equivalent resistance which is connected in case of series. So RS, resistance in series. Now we have according to Ohm's law, we have V is equal to I into R. Substitute this will be RS because we are connecting equivalent resistance. So substitute this equation 2 in equation 1. We have I into RS is equal to I into R1 plus R2 plus R3. So on deleting the common terms, we have Rs is equal to R1 plus R2 plus R3. So this is the combination of resistors in series, and this is very much helpful for you in order to calculate or in order to solve the numerical problem. So you'll have to know how do you calculate the connection of resistors in series values. So it is Rs is equal to R1 plus R2 plus R3. So how do you state it? The statement is, when number of resistors is connected in series, the equivalent resistance is equal to the sum of individual resistance. That is how you state it. The equivalent resistance in series is equal to sum of the individual resistance which is connected in series. That is all the statement for this combination of resistors in series. Now we are going to combination of resistors in parallel. How is that given? So here we have connection, or that is parallel connection, which is connected to a battery, and here we have one single connection, here is one single connection. So we have here three connections of resistors which is given over here. So potential is supplied, that is V is supplied here, and also current I is supplied. So we have current will move in a different path, I1, I2, I3. The current is getting splitted. So for this you can take an example of a water pipe. When you're dividing a pipe, or when it is a reservoir which is getting divided into rivers, it will be like it is not only moving in one single path, it moves in all three paths or all 4 or 5 paths. How many paths are there? It will move in all possible paths. In the same way here, there is not only one single path as in that of series, it is like a parallel. Parallel means there are 3 paths over here because we are considering 3 resistors. If it was n number of resistors, there are n paths. Okay, so here we have I1, I2, I3 which is flowing through a resistance R1, R2, R3. So when that is flowing, so we have here, that is the potential difference across it will be one and the same, that is V. So there the potential difference used to divide, but current used to be the same. Here current is getting divided, potential is same in this case. So same V is flowing across the connection. Total current flowing through the circuit is equal to sum of individual currents. That is, I is equal to I1, I2, I3. It's the same body, but it is getting splitted out. That's all. It's from the same place, but it is moving in different places, that is different directions, and it will come back to the original state, that is I again flows over here. Okay, arrow markers must and should for the movement in order to show the flow of electrons or flow of electric field, flow of current, flow of potential energy, whatever it might be in circuits. Arrow marks are must and should. Without arrow marks, you will lose marks. Okay, so now we have first point here, second point over here. Now it is our duty, that is total current flowing through the circuit is given as I is equal to sum of individual currents, that is sum of individual current is what? I1 plus I2 plus I3. So we know that according to Ohm's law, V is equal to I into R. So we have I over here. So V divided by R is equal to I. Since V is a constant term and R is the one which is varying because we have R1, R2, R3, but V is just V itself. So we have I is equal to I1 can be written as V divided by R1 plus V divided by R2 plus V divided by R3 can be written over here. So this can be rewritten as on equating. That is we are giving the equivalent diagram for this. Instead of 3 connections, we are just giving 1 connection, so it is same as that of the previous diagram, that is in combination of resistors in series we had done. No, similar way it will be for resistors in parallel. So it is R and P, and this is a battery, and I is the flow of current through it, and V is the potential difference across it. Okay, now we have got this equation, I is equal to V into, you can just take the common out, 1 by R1, 1 by R2 plus 1 by R3, call it as equation 1. Since this equivalent connections are made, the equations turns out to be I is equal to V divided by R and P. Because we know that for the resistors in parallel connection, V is equal to I into Rp. So I stays there itself, your Rp comes down. So this equation we have got. Substitute equation 2 in equation 1, we have got V by Rp is equal to V into 1 by R1 plus 1 by R2 plus 1 by R3. So V and V gets cancelled. Final equation turns out to be 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is a final equation for the combination of resistors which is connected in parallel. So this is also helpful for you in the numerical cases. If you have got numericals in which the resistors are connected in parallel, it is very easy for you to calculate by using this formula. That's all about the combination of resistors in series and combination of resistors in parallel. Now next we are going to a concept wherein we are studying about what is meant by cell, what is meant by EMF, and what is meant by a internal resistance. So now, what is meant by a cell? Cell is a one which has got 2 terminals. I'm talking about this diagram which is represented by this symbol. Representation is given over here, one with a bigger line, one with a smaller line. Bigger line suggests it is positive, smaller line it says that it is negative. So cell is a source of energy which supplies positive, that is the positive charges, as well as the negative side, negative charges. Negative charges are known as electrons. So from there the electrons are getting drifted in order to produce an electric current, and the flow of electric field is through the positive side. So this acts as a source. One single positive charge and one single negative charge, together it makes a cell. But many positive charges, many negative charges which is connected as a link over here like this, then this constitutes a battery which is called as a battery. Cell is just one, fusion of cell is nothing but a battery. Okay. Next, coming on to the internal EMF, electromotive force, EMF, which is induced by the circuit. That is, the flow of electrical energy is nothing but the EMF. That about flow of electrical energy when the circuit is off. When the circuit is on, the flow of energy is known as potential, which is calculated across the terminals, and it is when the circuit is on. Only in on condition we have potential difference across the ends of any of the conductor, which is calculated with the help of a voltmeter. But when the circuit is off, how is that we calculate? Is there a presence of potential? Yes, there is certain energy called as electromotive force which is present within the battery. That is, battery is supplying, cell is supplying it when the circuit is off. So when the circuit is off, there is a electromotive force which can be calculated with the help of a potentiometer. That is all about the EMF what I am talking about, which is known as electromotive force. Nextly, it is about the internal resistance. We know what is meant by resistance. What is meant by external resistance? The one which opposes the flow of charges is called as resistance. But what is meant by internal resistance? That is the resistivity force, that is the force which battery itself is having within it. That is said to be the internal resistance. That is opposition which is possessed for the flow of charges by the batteries or the cell internally is said to be the internal resistance. So in today's class, we have studied about resistance at certain temperature, because of which we got to know what is meant by coefficient of resistivity, and we also have studied the power loss, how exactly the power loss takes place and what is the formula for the power loss used. And third, we have studied about the combination of series as well as parallel connections resistors, and we have derived an equation for it which will help us in numericals. And finally, we have studied about these, what is meant by cell, what is meant by EMF, and what is meant by internal resistivity in short. Okay, that's all for today. Have a good day. Let us all meet in our next class, in the next upcoming session, session 5 of the same chapter. Until then, thank you. Have a good day.